Hello, I would like to welcome you to Lecture 29 of 3N03. We'll be discussing in this lecture the oscillators, the concept of an oscillator, how we can use feedback networks to create an oscillator, and we'll discuss three types of these oscillators: the Colpitts, the Hartley, and the Armstrong oscillators. And there are so many other types mentioned in the book of Floyd. I recommend that you take a look at them as well. And this material is coming from chapter 16 from the book of Floyd. And I'll give you a couple of examples on how to do the calculations for these oscillators. We have seen in previous chapters how to create a square wave oscillator. For example, we did that before using op amps. And if you use an integrator in addition to a square wave oscillator, you are able to create a triangular oscillator. To create a sinusoidal oscillator, we can also use an amplifier. And any amplifier can be turned into an oscillator through feedback. The whole idea here, if you have an amplifier, this amplifier will amplify the input signal and then will create an output signal. If we take that output signal and at specific frequency, at specific frequency, we recreate the same input signal that created the output. In other words, we close the loop. So we have a feedback network. This one creates an attenuation. It receives the output from the amplifier, and then it creates some feedback signal to be fed at the input. So if this amplifier gives a gain of 100, the output from this amplifier will be 100 times the input. If this feedback network creates an attenuation of 1 over 100, then the output will be attenuated again to the same value at the input, and then gives you the same input signal, which in turn will create the same output signal. In other words, the input will create the output, and the output, after being attenuated, creates the input. This is the whole idea of creating an oscillator. And usually this feedback network, which changes the amplitude of the input of the output signal and it changes its phase, is usually frequency selective. So by doing so, we can have a sinusoidal oscillation created by this oscillator, this amplifier at a specific frequency. So two parameters to remember: the gain of the amplifier that you use, the voltage gain, we call this AV, and then the attenuation created by this feedback network, which we call B. So what's being fed back here is equal to V output multiplied by B. And we define something, the closed loop gain. The closed loop gain is simply equal to AV multiplied by B. And this AV multiplied by B should be equal to 1 in order to get oscillations. Meaning that after you amplify the signal and then you attenuate it, you obtain the same input signal that you had. In other words, the input creates the output and the output creates the input. And then this oscillator can keep on oscillating forever. And of course, this frequency, these feedback circuits are usually frequency selective, so this will happen at one specific frequency. We can implement an oscillator through two different mechanisms. The first one is to use a non-inverting amplifier, say like the one we had with op amps. So here, if you have a sinusoidal signal at the input and you have a non-inverting amplifier that gives a positive gain of AV, you get an amplified signal at the output that's in phase with the input. For example, if the gain here is equal to 10, then this signal will have an amplitude 10 times the input signal. Now, if you take that very same signal and then you feed it back through the feedback network, and then you attenuate it by multiplied by 1 over 10, you get only 1/10 of its value. So if this was 1 volt in amplitude, this is 10 volts. You take this 10 volts amplitude and then you attenuate it, and you get the same signal. It's in phase, still in phase with this signal here, but attenuated by multiplying it by 0.1. Then you recreate exactly the same input signal. So we say if the gain here is equal to 10 and the attenuation is 0.1, then the product of 10 and 0.1 is equal to 1. We call the product of AV and B, we call it the closed loop gain, and this should have a value of 1. In other words, the input creates the output, which is an amplified version of the input, and then the feedback signal will recreate exactly the input again. This is the condition for creating oscillations. The scheme shown here is using a non-inverting amplifier, so the output is in phase with the input and the feedback signal is in phase with the output signal. Okay, so in that case AV is a positive number and B is also positive. We don't need any phase shift here in this case. The second type of oscillator we can build is also using amplifier, but we'll use an inverting amplifier, say like the common emitter amplifier we discussed, or the common source amplifier. These amplifiers usually give very high gain, but they also give you a phase inversion. So if this is your signal at the input, the output is an amplified version of the input, but with a phase shift. You can see this one looks like a negative sign, while this one looks like a positive sign. So we got amplification, but we got also phase inversion. So if the gain here is equal, say, to -10, this one has an amplitude of 1 volt. This one will have an amplitude of 10, but with a phase inversion. Now if you take this output signal and you pass it through a feedback network that attenuates the signal and also gives a phase inversion by 180 degrees. So if the gain here was -10, the attenuation here will be equal to minus 0.1. In other words, if this signal has an amplitude of 1, the output signal will have an amplitude of 0.1, but with a phase inversion. So here the gain AV is -10, and here I can simply call this a gain or attenuation. The attenuation is -0.1. You reduce the amplitude to 1/10, but you also add phase shift. And as a product, as a result of this amplification with a phase shift and then attenuation with an opposite with a phase shift but with the opposite ratio, you end up with the same input signal. So in that case, the product of -10 and -0.1 will give you 1 again. In other words, the output is an amplified version of the input, and the feedback signal is an attenuated version of the output, and then it recreates exactly the same input signal. And mathematically writing it, this is what we have. The product of the gain of the amplifier and the attenuation of the feedback network will give you 1. This can be -10, this is going to be -0.1. So this is how you can implement an oscillator using an inverting amplifier. So if you have an oscillator, how does an oscillator start oscillations? Well, when you turn on power to any circuit, you are actually injecting a step. If you take a look at the power, you are injecting, you close the switch, then the supply voltage will change from 0 up to 5 volts, say. This step actually contains all the frequencies. All the frequencies that you can imagine are in this step. So this circuit will amplify, this condition for oscillation will happen only at one specific frequency, because this feedback network is frequency selective. And as a result, only that frequency will be amplified by the ratio EV, will be attenuated by the ratio B, and then the product of AV and B will be 1, and then you get the condition for oscillation satisfied, and then the oscillations will start to pick up at that specific frequency. Of course, in the very beginning, the oscillations are very weak, and for them to pick up, usually they try to make AV multiplied by B a little bit greater than 1. So we call this closed loop gain, ACL. We try to make the closed loop gain, AV multiplied by B, a little bit higher than 1 at startup, to make sure that oscillations will start to pick up gradually and slowly before they reach a steady state. The theory that I explained can be implemented using many circuits, including op-amps, including MOSFETs, including BJTs, including JFETs. Many of the amplifier circuits we discussed can be used to implement oscillators. I will illustrate here the technique for using BJTs. So here we have, this is a common emitter amplifier. We have seen this one before. It's a common emitter amplifier. When you do the AC analysis, the emitter is shorted to ground. You're applying your input at the base. You're taking your output from the collector. But instead of using it as an amplifier, we'll use it as an oscillator. So we take the output from that amplifier, we feed it back through this tank circuit, and then the feedback signal will go back again as an input to the amplifier. Now the key analysis here is to understand how this tank circuit works. This is an inductance L, and it is in series with two capacitors. So if you try to see here, I can try to plot this one for you. At resonance, there is some current flowing inside the circuit. Okay, I'll call this current I here. Okay. Notice that at resonance, looking into this circuit, you see an infinite resistance. And this is known if you studied before LC circuit. So if you have an LC circuit, looks something like this, and L in parallel with C. At the resonance frequency, looking into this circuit, you see an infinite resistance. Okay, so this means that you do not really draw any current from this output. You are only sensing the voltage. Okay, so at resonance there is some current flowing here. Okay, and this current, you can see it creates some voltage drop across this capacitor C1. It creates some voltage drop across the capacitor C2. Okay, notice that the voltage drop across the capacitor C2 is simply equal to the current multiplied by the impedance represented by C2. This voltage drop here must be equal to V out. So the current will be adjusted in this loop. This current I will be adjusted such that I multiplied by the equivalent impedance of this capacitor, which is 1 over j omega C2, will be equal to the output voltage. Now, the feedback signal, this is my feedback signal between here and here. This is what I'm feeding back to the input again. The feedback signal is equal to minus I multiplied by the impedance of the capacitor C. Okay, notice the way the current is flowing. It's flowing from the ground to this terminal, while VF is assumed to be from here to here, so the phase inversion. So here I can simply say that VF, the feedback signal, is equal to minus I multiplied by the impedance represented by the capacitance C, which is 1 over j omega C. So now we know the ratio between the feedback signal to the output signal. This ratio is what we call B, is the ratio B we are looking for. Okay, so just remember that the ratio B here I'm going to be using is the voltage VF over V out, what I'm feeding back to the output. This is what I'm feeding back, and this is my output. And because the same current is flowing in both of them at resonance, you can simply write this same ratio as minus I multiplied by XC2 over I multiplied by XC1. And remember, XC2 and XC1 is the impedance represented by the capacitor. Actually, I should correct this one here. This is I. The feedback signal is simply determined by the capacitor C1. So this should be minus I multiplied by XC1. So I have to correct this one here. And for the other one, the output signal is simply equal to I multiplied by XC2. So this one as well have to be corrected. This have to be also here. I can write that as 2 here, not as 1. Okay. So this is what we have, and so you can see that the ratio will depend on minus XC1 over XC2, which is really the opposite of the ratio of the capacitors. So this will determine for us how I should select these capacitors in order to bring the proper feedback signal. Now, one thing to remember, that during resonance, this inductor is in series with these two capacitors. So the equivalent capacitance is a series combination of both. This is why the total capacitance is written in this form. If you remember from your basic circuit analysis, capacitors, when we connect them in series, they have an expression similar to resistances in parallel. So this is why you get this expression for the total capacitance, and this is the frequency at which this tank circuit will resonate. And at that specific frequency, the impedance seen into this tank circuit will be infinite. So this summarizes the steps I mentioned earlier. We have some inverting amplifier here, AV, and then I have this tank circuit. It feeds back a part of V out. This is called VF. This this now my input signal. This is what's being fed back again to the input. Remember the ratio between the feedback voltage to the output voltage is minus I x C1 over I x C2, and the I is simply the current circulating in this circuit. And as I explained to you, at resonance, there is no current flowing from the output here, and we assume there is very little loading coming from the input here. So this circuit is resonating in its own. There is a current flowing through it at resonance. Now, the ratio between XC1 to XC2, XC1 is the impedance represented by the first capacitor, which is 1 over j omega C1. XC2 is the impedance represented by the second capacitor, which is 1 over j omega C2. So our attenuation ratio B is minus C2 over C1. So if this amplifier gives, say, a gain of minus 10, then I would like this attenuation ratio to be equal to minus 0.1. So C2 will have to be equal to 0.1, the value of C1. Okay? In order, if this gives you a gain of minus 10, I have to have an attenuation of minus 1, so that the ratio between AV and B is equal to 1. Then the input creates the output, and the output creates the input. Okay? And this is what you have here, that the closed loop gain must be equal, which is the product of AV and B, must be equal to 1. Then the gain of this amplifier must be opposite to the attenuation. If this is minus 10, this will have to be B will have to be minus 0.1. And remember that B is simply equal to the ratio of minus C2 over C1. And this means that the amplification ratio of the amplifier should be minus C1 over C2. This is really the analysis of this Colpitts oscillator, which uses an inverting amplifier and then a tank circuit in the feedback that has one inductor and two capacitors. Okay, let's take a look at an example. We have here, this is a common emitter amplifier. We feed back the signal from the input through this tank circuit, and then we feed it back as an input to the amplifier. So this becomes an oscillator. The value of this inductor is 50 millihenry. The value of these two capacitors, C2 is 0.01 microfarad and C1 is 0.1 microfarad. Remember that the attenuation ratio that you're going to be looking at is minus C2 over C1. Okay, so we can calculate the value of B, and once we know the value of B, which is going to be minus C2 over C1, which is minus 0.1 here, this means that we should have an amplifier of gain of minus 10 in order to get oscillations starting here. Okay, of course the amplifier gain should be a little bit higher than minus 10 in order for oscillations to pick up in the beginning. Okay, but as a number, we can simply say that minus 10 it should be the value of this amplifier, even though they may try to make it a little bit higher than minus 10 for oscillations to pick up. So we did analyze this circuit here before. The B is equal to minus C2 over C1. So it's minus 0.01 microfarad over 0.1 microfarad. So B is equal to minus 0.1. And immediately this means that this amplifier must give you a gain of minus 10. So these are the steps I mentioned earlier. The total capacitance represented by these two capacitors determines the frequency of oscillations. It is simply 0.1 microfarad by 0.01 micron divided by 0.1 plus 0.01. And remember here, two capacitors connected in series have an expression similar to two resistors connected in parallel. Anyway, this will give you a total capacitance of 0.0091 microfarad. Now this tank circuit, which is composed of an inductor in series with two capacitors, have this resonance frequency 1 over 2 pi square root L C total. If you plug in the numbers for the inductor, which is 50 millihenries, and the value of the total capacitance, you calculated 0.0091 microfarad, and you get this frequency of oscillation 7.46 kilohertz. So this circuit will oscillate at 7.46 kilohertz. As I mentioned earlier, the attenuation ratio that we have is simply the ratio of minus C2 to C1, which is minus 0.01, which is minus 0.01 over 0.1, so it's minus 0.1. So the gain of the amplifier must be the opposite of the attenuation ratio B. So it's minus C1 over C2, so it's minus 0.1 microfarad or 0.01 microfarad is minus 10. So this is the region or the condition for this circuit to have stable oscillations. Usually you try to make it a little bit higher than minus 10 to have the oscillations pick up at the beginning. A second type of oscillator is called Hartley Oscillator. Hartley Oscillator has exactly the same concept of operation as the Colpitts Oscillator. The only difference is that instead of having one inductor and two capacitors, we have one capacitor and two inductors. But the concept is the same. At resonance, this is a tank circuit, no currents flowing in. You ignore the loading from this circuit. You assume that the input resistance is very high. Then there is a current circulating in this loop. It's resonating. Okay. The output the output voltage is simply equal to I multiplied by the impedance of this inductor L2. The signal that's being fed back into the input is equal to minus I multiplied by the impedance of this inductor. And in that case, your attenuation ratio is VF over V out will be equal to minus L1 over L2. Notice that in the capacitor case it is the opposite, okay? Because of the impedance of a capacitor is 1 over J omega C, while the impedance of an inductor is J omega L. So by doing so, we know what is the attenuation ratio. We know what is the resonance frequency. Resonance frequency is simply 1 over square root C multiplied by L total, and the L total here is L1 plus L2 because these two are in series at resonance. Because at resonance, this is how the circuit looks like. There's a current flowing in this loop. So we know what is the resonance frequency. If I know C5, L1, and L2, I know what's the attenuation ratio be. It is minus L1 over L2. I know what should be the gain of this amplifier. It should be the opposite of the attenuation ratio, so it's minus L2 over L1. So I know everything. It's exactly identical to the Colpitts Oscillator, but the only difference that we use two inductors, not two capacitors. Okay, a third type of oscillator I would like to mention here is called the Armstrong Oscillator. And this Armstrong Oscillator has exactly similar concept. We have here, this is a common emitter amplifier. You take the output from the common emitter amplifier and then you pass it to a resonance circuit. So you have an inductor and you have a capacitor. But this inductor is the primary of a transformer. Okay? So, and if you remember from your studies in circuits, a transformer usually is a structure that has two coils, and they share the magnetic flux. So the magnetic flux in one of them links to the other. So, and you have different number of terms. There is number of turns in the primary and number of turns in the secondary. Okay. So, for example, you can have here 100 turns in the primary, and they can have only 10 turns in the secondary. This means that this is a step down voltage. The voltage at the primary is 10 times the voltage at the secondary. This is what we have here exactly. We have a secondary coil, but notice also these two dots. These two dots are telling you that this is not only a step down transformer. So you may have 10 volts here, you get 1 volts here, the amplitude I mean, but you get also phase inversion. So what you're getting on this side, the output from the secondary coil is out of phase from the primary coil. And here we have two conventions for coils or for transformers. You can find something like this, and they draw two dots like this. This means that they are in phase. This may be 10 times the number of turns of this one, but the attenuated signal at the secondary is in phase with the signal at the primary. Okay, this is one of them. And the second type of transformer you can get is this, where you draw the primary this way and you draw the secondary this way, and then they put opposite dots. You can put opposite dots. These opposite dots simply tell us that the primary and the secondary are out of phase. Yeah, you are stepping down your voltage or stepping it up, it doesn't matter, but you are also adding a phase inversion by 180 degrees. So this is what we have here. So this amplifier gives a gain of minus 10, and this transformer gives you an attenuation of minus 0.1. Then you close the loop in the same way. The product of AV multiplied by minus B by B here is going to give you 1. This gives you a gain of minus 10. This gives you an attenuation of minus 0.1 of B minus 0.1, because this one here has 10 number the turns of this one, and there is a phase inversion. Then the product of AV will close the loop, and then the input creates the output, and then the output creates the input, and then your loop is closed. Now The only difference here is that you have a resonance circuit that's formed by this capacitor and the primary coil, and the resonance frequency of this tank circuit, still a tank circuit, it resonates at that frequency. It's 1 over omega is 1 over square root C1 multiplied by L primary. L primary here is the inductance of the primary coil. So and as I mentioned to you, we are feeding back the signal. This is the feedback signal, and this is the output signal. Okay, and the ratio between the feedback to the output depends on the number of turns and the secondary to the primary. And remember, there is a phase shift because of these opposite dots. So this feedback ratio is VF to V out. It's minus the number of secondary turns to the number of primary turns. And we call this number here minus N. So if this ratio here is minus 0.1, if this N is 0.1, so this whole ratio is minus 0.1, then this amplifier must give you a gain of minus 10. And this is what I say here, that AV, the gain of the amplifier, the voltage gain of the amplifier, must be opposite to the attenuation ratio, must be equal to minus 1 over N. So if minus N is 0.1, then AV must be equal to minus 10. Okay, let's take a look at an example. We have here a common emitter amplifier with a voltage gain of 10 is available. So remember, a common emitter amplifier gives you a gain with a phase inversion. So even though I write it as 10, remember the gain really is minus 10. This is the modulus of the gain. Find the turns ratio N of the needed transformer to build an Armstrong oscillator. So we need to build an Armstrong oscillator using this amplifier. If the desired resonance frequency is 10 kilohertz, find the inductance L primary, the inductance of the primary coil L primary, to be connected to, in parallel with a capacitor of 0.1 microfarad. So we know what is the capacitor that's going to be connected in parallel with the primary coil. We need to know what is the inductance of the primary coil, but we know the resonance frequency. I know the resonance frequency, I know the capacitance, and I know what is the inductance. So this one I can solve for. I also can determine the number of turns ratio, because the gain of the amplifier is simply minus 10, and the number of turns will have to give you the opposite of that gain. Minus n will have to be equal to minus 0.1 in that case. So we are able to determine n will have to be equal to 0.1. So here we can put all this together. This is an inverting amplifier. The actual gain is minus 10. Then the attenuation of the transformer must be minus 0.1. But I removed the negative sign from both of them. So I took the absolute of the gain. We know that the amplitude of the gain, the absolute of the gain is 10. Then in that case, the number of turns, the number of turns ratio, the secondary to the primary, or the second to the primary here in this case, will have to be opposite to that number, will be 0.1. So the amplifier gives a gain of minus 10. The transformer must give you attenuation of minus 0.1. Then the number of turns of the secondary must be equal to 0.1 number of turns of the primary. Okay? So this will solve the first part, what type of transformer I should be using. Now, what is the inductance of the primary coil? I know the resonance frequency. I know the capacitance connected in parallel. I can solve for the primary coil inductance. I can simply square both sides and write L primary as 1 over 4 pi squared C1 F naught squared. If C1 is given as 0.1 microfarad, F naught is given as 10 kilohertz. If you do this calculation, you end up with 2.5 millihenry. So we can determine what is the inductance of the primary. We know the number of turns of the coil we have to use. We know the gain of the amplifier. We can build that Armstrong oscillator. The only difficulty with this Armstrong oscillator is that it requires a transformer. And using a transformer is not usually a desired thing in oscillators. So usually I would say the Colpitts is the one that's most commonly used, because it's very easier to control the value of capacitances rather than to control the value of inductances, and also because it does not require a transformer.